Alright, so section 3, related rates. Activity 1 is area and volume. Okay, so related rates. This is the rate at which something changes, of course, with respect to time. I.e., the rate, so in this first example, we're doing circumference and radius, okay? So instead of area, we're actually more concerned with and circumference. Okay, so the rate at which the radius changes will impact the rate at which the area changes, right? If you change the radius, if you increase the radius, you're going to have a bigger circumference and you'll have a bigger area, right? Smaller radius, smaller circumference, smaller area. Okay? So our first comparison is going to be with circumference and radius, okay? So if the radius is changing at a certain rate, what happens to the circumference? So anytime that we have something changing, you guys need to think of derivatives, okay? The rates of change. So if we want to find the radius at which the circumference is changing, what do you think we want to find?
The derivative?
Yeah, exactly. So like C prime is what we want to look? Yeah, absolutely. Okay, so, and we're going to be differentiating this with respect to time, right? So, let's differentiate the whole thing. So, derivative of C is equal to 2 pi r with respect to time. Okay, and just like we've been doing, like you guys have been doing with implicit differentiation, right? We're going to take the derivative of each thing. Are you okay? Kids these days. Okay, so take the derivative of C with respect to time. We'll take the derivative of 2 pi r with respect to time as well. Okay? Now, just a note here, because 2 pi are constants and the ratio of, or like the relationship between radius and circumference is not going to be changing, right? The ratio of circumference to the radius is always going to be 2 pi r, right? Circumference is 2 pi r. So we're not going to differentiate the 2 pi, okay? Because as, like we're still gonna have that same ratio no matter what. Like the ratio for radius to circumference is always 2 pi r, okay? So if the radius is changing, the circumference will be changing, but not the 2 pi. That ratio is still legit, okay? So we're gonna leave that one alone for now, okay? Is that all good? Yeah? Okay. So, derivative of C with respect to T, we can abbreviate that for C prime, okay? And that is equal to 2 pi, and then if we differentiate R, we'll just have R prime. Okay? Good. So, just a little note here. And I'm going to jump up a little bit. Okay, so just a note here. So at this point here, so C prime is equal to 2 pi times R prime. So the rate, so this is the rate of change of circumference, which you guys said earlier is C prime, right? The derivative is 2 pi times the rate of change of r, which is r prime, with respect to time, WRT, with respect to time. Okay, so that's what this formula is saying here. The rate of change of the circumference is 2 pi times the rate of change of the radius, which is r prime. Okay, so for example, if the radius is changing at a rate of 7 centimeters per second, so if r prime is equal to 7 meters per second, what is c prime? So what would I do?
2 pi times 7.
2 pi times 7, yeah, exactly, right? We're just going to substitute that into here. So c prime is equal to 2 pi times 7 centimeters per second, and 2 pi, I don't know why I got to 14 pi, actually, yeah, 14 pi makes sense. 14 pi centimeters per second is the rate at which the circumference changes. Okay? All good? Groovy. Okay, so a circular disc is heated then cooled. During the cooling process, the radius is found to be decreasing at a rate of 0.02 millimeters per second. So the radius is decreasing at 0.02 millimeters per second. At what rate is the area of the disk changing? So what is my A prime? When my radius is equal to 100 millimeters. Okay, so we are asked, what is the area, or how is the area changing as the radius changes? So what is my formula for area of a circle?
A equals pi r squared.
Yeah, excellent. Pi r squared sounds like area to me.
Oh, yeah.
When I need to find circumference, I just use pi d.
Aaron knows that song.
We just finished the circles in grade 7. So I like that song now too.
Did you actually teach it to them?
Yeah. Well, I didn't teach it,
That's so
I just
cute.
showed them the videos. Yeah. Yeah, it was really nice. Actually, we were just like doing it, and Mrs. Dalloway comes in, she's like, have you heard of this circle song? I'm like, no. And then she showed him, like, oh, sweet. And then there's a hip hop version too. It's pretty sweet.
Fricky fresh.
Yeah, exactly, right? Okay, so as Quinn mentioned, we know area is equal to pi r squared, right? And we are looking for A prime, right? We're looking at the rate at which the area is changing. So what do we need to do? Let's take the derivative, right? Good. So we'll take the derivative of the whole thing. So derivative of A pi r squared with respect to time. Okay, so then we'll do derivative of area. And then again, we're going to leave the pi alone. And then we're going to do the derivative of r squared with respect to t. Okay, so the derivative of area is equal to A prime, which is equal to, again, we're just going to leave that pi alone because the relationship between radius and area is still going to be pi r squared, right? So we'll leave that alone. And now we'll take the derivative of r squared, which is going to be 2r. Yeah. Okay. 2r times, don't let me forget the r prime, right? The rate of change. Okay, so I'm just going to rearrange that. So A prime is equal to 2 pi r times r prime. Okay, we know our R prime is decreasing at negative 0.02 millimeters per second, and we know our radius is 100 millimeters. So let's just solve, substitute, and solve. So A prime is equal to 2 pi when our radius is 100 millimeters, multiplied by the rate at which our radius is changing, negative 0.02 millimeter per second. And this is a millimeter. Okay, so punch those in. So 2 times 100 is 200 multiplied by 2%. So 2%, 100 is going to be 2 multiplied by that 2. And that's a negative, so A prime is equal to negative 4 pi millimeters per second squared. Millimeters squared per second.
Oh,
Right, because it's area.
yeah. I put second squared.
Oh, that's like acceleration, right?
Yeah.
Yeah. Okay, is that alright? So not too bad. Just like implicit differentiation is essentially what this is, right? Does that work out, Sam? I'm assuming that's what you're doing.
Yeah.
Should work. Okay, example 2. So water is being poured in an aquarium. This is fun. It does?
Yeah.
Good. Okay, so we have an aquarium. Sometimes it might help you guys to draw an image. Other times, if you're like me, your image can just ruin everything. This is not how I drew it. Actually, no, that's actually okay. That can be a dotted one. Yeah, that's okay. You know what I'm gonna work on this whole summer? Working 3D or drawing 3D shapes.
How do you draw it in 3D?
I did a square here, and then you draw a square back here, and then you connect them, and then this one's a dotted.
Or you just, like, I always just like, I just do like this, and then you do these 2 lines, like these 3 lines, and then connect them like that. There you know.
How do you do it?
Like, so you just do a square,
Like this?
yeah, and then you do 3 lines, 1, 2, 3, and then you draw like straight lines to connect them, yeah.
What about this one?
And then you should have made that one a little bit shorter, but then you connect it to the top one, so like that, yeah.
I see.
I like
Oh,
mine.
that's actually really good, Quinn.
Mine's
Wow.
like the exact same as yours, just with it like this.
That's amazing. Let's get rid of that other trash one.
I don't wanna
Thanks, Quinn.
flex on everyone or anything, but I am superior.
The best
Whoa.
3D object
So
drawer
bold.
in this room. What is your supply? Yeah, he's actually pretty good too. I think I'm the worst. Yeah, mine's the worst.
At least I drew a fish in mine,
Oh,
as well as glove. So
glove?
yeah, like you know how fishes go like glove,
The fish says glove?
glove, yeah.
Awesome.
Okay.
Okay, so this is
Shut up, Sam.
our aquarium. Okay. Water is being poured into an aquarium, which is 60. So I have 60 long here. I know it doesn't really look like it, but you gotta use your imaginations. Our length is 30 and our height is 40. Okay, not to scale.
Wait, why don't we just switch the 60 and 30?
Yeah, you can do
Oh, that actually is Sam.
the 60 and the 30. Yeah. I don't know. This is just how I had it set up. Okay. And again, if you're ever like in an assessment and you're worried about how you're setting it up, just be clear. Okay. Just be clear. Just label your sides. Okay. But yeah, so we want our depth level of the tank and our width. Okay. So water is being poured into an aquarium, which is 60 by 30 by 40 centimeters. What is the relationship between the rate at which water is being poured So water is being poured, and so water being poured. What do we, when we think of water being poured, what do you think of? Do we think of volume or do you think of height? The rate at which water is being poured. Volume, okay, good. So that is going to be our volume. And the rate at which the depth is increasing, that's going to be our height. Okay? And we know that this whole thing is 40, right? Okay. So, our width and our depth. Okay, our width and our depth. Is this ever changing? Sam and Emma both say no. And I'm sure Quinn is pondering still.
No, it's not.
It is not changing, exactly, okay? So, but what is changing?
The volume of water.
Yeah, the volume is changing, and what else is changing?
The height of.
Yeah, the height is changing, right? So, volume of a cube is what?
Yeah.
Length times width times height.
Yeah, length times width times depth, say? Length times height times depth. Yeah, let's do length times height times depth. And they're all kind of interchangeably, right? So I said this is my length, this is my depth, and this is my height. Although the H is not 40, right? That's just the height of the aquarium, right? That's not the water level, that's just the height of the aquarium. Okay, so, and what did we say what was changing? Only H, right? So, this, my length and my depth is not going to be changing. So I'm just going to rewrite this now. So volume is equal to 30, which is my length, times my depth, which is 60, multiplied by the height, right? Which is changing. Now, anytime that something is changing, you guys are thinking of
Derivatives.
derivatives, right? So let's differentiate. Okay, so derivative of v is v prime, right? These two values, 30 and 60, are they changing?
No.
No, so let's just leave those alone. Actually, we can multiply them together. So 3 times 6 is 18, add our two zeros, 1800, and the derivative of h is h prime.
What? So you just add the zeros on the end?
Yeah,
Since like.
Yeah.
Yeah.
We talked about this.
yeah,
That's ridiculous.
So-
yeah.
Alright.
Yeah, so 3 times 6 is 18, and then you have 1 0 on
How
each.
could you do 30 times 60?
My calculator, or I'd think like. Oh.
60 times 3 times 10, maybe?
Yeah.
Wow.
Yeah. But yeah, you can just do that, multiply the numbers in front and then add the zeros, yeah. Cool.
That's upsetting.
I love that. Okay, good. So, what is the relationship between the rate at which water is being poured and the rate at which the depth is increasing? Have we solved it? No?
Yes?
Yeah.
The relationship that's all together.
Yeah, right? And that's really all that we're being asked here, right?
Yeah, and it says what is the relationship?
And this is it.
Guys.
This is the relationship right here.
Could we find the actual rate at which the water? No, we have to be given something, right?
Yeah, if we knew the rate at which the height is increasing, we could find the rate at which it's flowing or filling up, or vice versa, right? Yeah, for sure. And we will actually solve one this next question here. Okay, so a funnel. Fun. Ha. Okay, so a funnel. This is how we draw a funnel. Okay, draw a circle. Okay.
I don't have
I don't. I had to YouTube it.
Okay, Sam. None of us are like you.
Something like that. Probably make your funnel a little bit straighter than mine. This kind of looks like a shaved ice cone that has been in the sun for too long. Actually, that's better. It's not the best, but that's okay.
Yeah, no,
Okay?
What do you mean upside down?
Because like a cone points upwards.
Oh, I guess it.
No,
Yeah,
that'd
it
just be a regular phone.
Because
No.
if you have a cone, that's an ice cream cone.
Yeah, but what about a party hat? That's also a cone,
Sure is.
Yeah, but
Oh.
it goes on top of your head.
which is upright.
Yeah.
So it's not upside down.
What is the right way for a cone?
It's definitely pointing the
Up.
Up.
So it can stand
right towards the
Yeah.
heavens.
Yeah. towards the heavens. Okay, so we have a funnel, aka
Ice cream cone.
upside down
Upside down cone.
cone, aka ice cream cone. Anything else?
Mm,
Uh,
inverted party hat.
Ooh, nice.
what
I
else?
found writing this down.
Yeah, make sure you write this down.
Oh, it could be like a underwater volcano.
We're really reaching here.
Yeah.
Haven't you seen those though?
Do they point this way?
Yeah.
Really?
Well, some, you know that one volcano that's like blue?
No.
Oh, if you look it up, you'll see.
Blue volcano.
You know those diagrams
I
that
think it's by
show.
like Yellowstone.
We should look at it after.
You know those diagrams that show your peripheral vision.
Yep.
Coming out of an eye.
Yeah.
It kind of looks like that, but sideways.
Or like those things that you hold up to your mouth and then you like talk and it's like loud.
The megaphones.
Oh, megaphone, yeah.
Great. Okay, so we know a few things.
we know cone shaped things.
I think ice cream cone is the best part of these. Waffle cone or sugar cone?
Waffle.
I get mine in a cup.
What?
Yeah,
What?
cup.
Sorry.
What?
Sorry.
I agree with you.
Yeah. The ice cream cone's the best part,
You
especially
get your
if you
hands
put
all
bottom.
sticky.
Yeah, that's half the fun.
Only if you're not slow eater.
Oh yeah, well said, Sam. Okay,
I feel
radius
so hurt.
of 10, height of 15 centimeters. Liquid is drained from the bottom. Let's say we have a green fluid. I used blue, but I already used blue there, so
Gross is floating.
green fluid. There used to be this show called Uh-Oh. And like it was like a TV show, it was a game show for kids.
Mm.
And they would go up and part of it they would get like slime dumped on them. I don't know what it was actually made of, but it looked pretty gnarly. We'll pull that up too. We got a lot in the parking lot.
Uh-oh.
Uh-oh.
I like the way you said that, Sam.
Uh-oh.
Okay, so this whole height is 15 centimeters, right? But we care. Oh, and we know the rate. So liquid is drained from the funnel. So V prime is negative 12 centimeters cubed per second. Okay, when the height is 5 centimeters from the bottom, find the rate at which the level of the liquid is falling. Okay? So, formula for volume of a cone. You guys are not expected to memorize these. I have a formula sheet. I just have to print them and give them to you.
Isn't it like? No, never mind.
Go
There's
on,
one
give
half,
it a stab.
One, no? There's a number in it, right?
3.
Yeah, 1/3.
Oh, I was close.
1/3 pi r squared h.
Hmm.
Nobody knew that off the top of their head?
I knew there was a fraction in it. I
Just to know how much volume of, ice cream. Well, you're a cup. Never mind.
Except I worked in an ice cream shop, so I know all of it.
Yeah, so I was
Oh.
actually kind of informed.
So I knew that.
They like make you learn this on the first day.
Just basic level calculus, just do ice cream.
Okay, let's look at that formula that we have up there. Formula for ice cream cone.
Yeah.
1/3 pi r squared h. How many variables do we have in there? And let's just look at this side of the equation. So forget about that.
2.
2. Do we like 2 variables?
You bet we don't.
No, we don't. We do not like 2 variables. So we need to relate them in terms of one another. So I'm just gonna make a note here. So two variables need to write in terms of one another. Okay? So we can either write it so we have two R's, or we can either write it so we have two H's. Okay? That's what we have to do. So I'm going to solve for R. Solve for R. Not a pirate's favorite letter. You may think it is. But it's really the C.
Yeah.
Okay, so my radius to height ratio. So radius to height is equal to what? What is my radius to height ratio? What are my dimensions of my ice cream cone? 10 over 15, good.
Oh.
10 over 15. And we're going to solve for R. So multiply both sides by H. And then we get R is equal to 10 over 15. H can be reduced to 2 over 3H. Okay, so now we have H as our only variable, so we can substitute that in to this formula right here. Okay, so volume is equal to 1 over 3 pi. R is 2 over 3H squared times H. Okay, so we're just gonna clean this up a little bit before we take the derivative. Okay, it's gonna make our lives easier. So 4 over 3 squared, 1 over 3 pi. 4 over 3 squared is 4 over 9 times H times H. 1 over 3 multiplied by 4 over 9 gives me 4 over 27 pi, and then this is squared, sorry, and then H squared times H gives me H cubed. Four over 27 pi H cubed. Good. Are we okay? Yeah. What's next, Emma?
Taking the derivative.
Yeah, perfect. Let's take the derivative, indeed. So, b prime is equal to 3 multiplied by 4 over 27 pi times h squared. Don't let me forget.
H prime.
Yeah, nice. H prime, good. And from there, what else can I do to make this easier for us? We know something, and I picked up the green marker.
12 centimeters.
Yeah, we know our v prime, right? We know our v prime is negative. Let's unmute cube for a second. Okay. So what are we gonna do? What's next? We just gotta solve for h prime, right? And what else do we know?
The height.
The height, yeah, good. So we're gonna find, and what is the question asking us?
Find the rate at which the level of the fluid is falling.
So find h prime, right? When h equals 5. You okay?
Yeah, I just have to think of.
Oh no, my recording. Just kidding. Okay, now you're just being obnoxious.
Sorry.
It's okay. Okay, so we have 3, and I'm just gonna leave these fractions alone right now. Okay, pi h is 5 squared times h prime.
What I'm laughing.
Okay, so we get 12 over 27 pi times 25 times h prime, which is equal to negative 12. Okay, let's solve for h prime now, okay? So multiply by 27. Those will go away. We're going to divide by 12. Those will cancel. We're going to divide by 25 and pi. So that's gone. What's up, Emma?
You said that the numbers.
I know. But we're left with h prime. So we can be happy about that, right?
Where's the 112 one? Oh, over there. That's right.
You okay?
Yep.
Okay. So 12 and 12 will cancel. And then we still have that negative, so we get negative 27 over 25 pi is equal to h prime. So what? What does that even mean? Can somebody paraphrase this answer for me? You can hiccup, it's okay. No, don't. Please don't. I mean, like, I'm not tech savvy and I can't edit out those noises. That's okay.
Negative 27 over 25 pi is the rate at which the level of liquid is falling. Is it?
Yep. When the height is
5.
5, right? Because that makes a difference, especially for like a cone, right? Because obviously when we're like up at the top, the rate at which it's decreasing is going to be much slower than when we're at the bottom. Okay? Your gas, so yeah, let's finish up that. And as Quinn said, so the rate at which the height is decreasing.
Can I do it in decimal?
Yep. Is 27 over 25 pi. Oops. I got a little excited there. It's a double pi. Three-legged pi. Centimeters per second. Or if you want to calculate that, you get 0.344 centimeters cubed per second. When the height is 5 centimeters. And you guys should always like paraphrase, give a sentence answer for a word problem, right? Exactly.
I called for a lifted ice cream.